Let's continue our lesson in chapter 4, which is pumps and turbine. Okay, so in previous lecture, we have learned how to determine the head for the pump, for the actual head for the pump, and then from the actual head, okay, we can define what is the power produced from the pump based on that efficiency. Okay, and then in the last part of previous lecture we have discussed about the effect of pump when we install in series and parallel. Okay, so when the pump installed in series, we can see that the effect in terms of head, which is double head when pump installed in series, will be H equal to H1 equal plus H2. And then meanwhile for second operation, which is pump installed in parallel, the effect can be seen in terms of the flow rate Q, where Q parallel equal to Q1, which define Q from pump 1, plus Q2, which define Q, which is flow rate for pump 2. Okay, and then for this lecture we will focus on the dimensional parameter and similarity or similitude analysis or law. Okay, so why we need to study about this dimensional parameter? Okay, because all the characteristics of pump are usually determined experimentally, so it is expected that dimensional analysis and similitude consideration will prove to be useful in the study and documentation of this characteristic. Okay, so from the previous lecture, we have learned that the principal or dependent pump variables are the actual head rise, which is HA or H pump, HP, and then we have learned about W dot shaft, which is shaft power, and then efficiency. Okay, so we expect that this variable will depend on the geometrical configuration, which can be represented by some characteristic diameter, which is D, or other pertinent lengths, which is length, and then surface roughness. Okay, so in addition, the other important variables are flow rate Q, and then the pump shaft rotational speed omega, and then fluid viscosity mu, and the last one is fluid density. So this is all the variable that is depend uh, that is how to say that there is a variable that we have learned in previous lecture. Okay, so for this lecture we will only consider incompressible fluids presently, so compressibility effect not need to be considered. Okay, so as you can see, this is the example, the dependent variable in terms of W dot, which is W dot shaft, and then N or omega. N is rotor speed, or omega, because omega basically equal to sorry omega basically equal to 2 pi n. Okay, so n or omega, so it represented. M is angular velocity, n is rotational speed, d is diameter, okay, q is flow rate, delta p is pressure drop, rho density, and mu is viscosity for the fluid, as I mentioned before. Okay, so this can be described in terms of the dimensional or dimensionless parameter. So dimensionless, I think all of you already learned in MSc 441 about the dimensional parameter, and then you have learned about Buckingham's pi theorem. Okay, so the first one is power coefficient. So the first one is power coefficient, which is known as CW. Uh, CW dot. CW dot equal to W dot shaft divided by rho n power of 3 d power of 5. Okay, so it is also equal to W dot shaft rho omega power of 3 d power of 5. Okay, so n is rotational speed, omega is angular velocity. Okay, so we can use omega equal to 2 pi n. Okay, and then the dependent pi term involving the head is usually expressed in terms of ch, so it is not written here. So first it is about the head rise coefficient. Okay, so head rise coefficient. Okay, so head rise coefficient, which is ch, ch equal to GHA, which is gravitational acceleration multiplied with the head for the pump over omega square d square, or also equal to GHA omega equal to n square d square. Okay, so we define GHA. So as you can see, GHA is the actual head rise in terms of energy per unit mass. Okay, so GHA is basically actual head rise atau actual head for the pump, actual head rise in terms of uh, energy per unit mass. Okay, and then sometimes we just we just define actual head rise in terms of HA. So HA is energy per unit weight. Okay, uh, and then the second one is CP, or C power. The dependent pi term involving the shaft power is expressed as CP or CW dot, as you can see here. Okay, which is omega dot shaft divided by rho omega cube, and then d power of 5. Okay, so that is the power. We call it as a power coefficient. Okay, and then we have a pressure coefficient, which is Cp delta P divided by rho n square d square, and then the last one is flow rate coefficient, which is Cq equal to q over nd, or omega d power of 3. Okay, diameter power of 3. And then the final dependence parameter Python is the efficiency. So but basically the efficiency is already dimensionless. Okay, so how to obtain the efficiency? Okay, so efficiency equal to rho g qh. Okay, so this is efficiency of pump, which is rho g QH divided by W dot shaft. Rho g QH is power for the fluid divided by power produced from the shaft, which is defined as efficiency. So rho g QH also basically equal to CQ multiplied with CH divided by CW W dot. Okay, so if you rearrange that term, you can get rho g QH over W dot. And then not to forget about the Reynolds number. So Reynolds number plays an important parameter for study for this chapter. Okay, so the last item in each of this equation is a form of Reynolds number. As you can see, this is Reynolds number. Okay, so this is Reynolds number. Which is a form of Reynolds number that represent the relative influence of viscous effect. So this is viscous effect. When the pump flow involve high Reynolds number, as usually for the engineering case, experience has shown that the effect of the Reynolds number can be neglected. Okay, for simplicity, the relative roughness, which is relative roughness, which is over D, can also be neglected in pump, since the highly irregular shape of the pump chamber is usually the dominant geometric factor, okay, rather than the surface roughness. So this is all the last one is related to flow coefficient, which is CQ. CQ equal to Q and Q and D over 3, or Q omega D power of 3. So this is called flow rate coefficient or flow coefficient. So if we have all these coefficient, okay, so we can come out with the similarity or similitude analysis. Okay, so what is similarity? Let's say if we have two pumps from the same coming from the same family, are operated at the same value of flow coefficient. Okay, so what is similitude analysis? Okay, so this is a similarity relationship between any two pumps. Okay, so let's say you have two pumps. Okay, let's say you have two pumps, and then we want to define based on flow coefficient. Two pumps defined in terms of flow coefficient. Okay, so flow coefficient, which is Q omega dq 1 equal to Q omega dq 2. Okay, so this is similitude analysis. Okay, so if you want to define in terms of head rise coefficient or power coefficient, you just for example, in terms of head coefficient, head rise or head rise coefficient, you can come out with GHA over omega square d square pump 1 equal to GHA omega square d square pump number 2. Okay, and then in terms of power coefficient, in terms of power coefficient, W dot shaft rho omega 3 d power of 5 pump 1 equal to omega dot shaft rho omega 3 d power of 5 pump number 2. Okay, so this is the similarity relationship. So where the I repeat, subscript 1, okay, 1 and 2 refer to any two pumps from the family of geometrically similar pumps. Okay, so we just, for example, change the rotational speed, change the n, the rotational speed, or omega, which is the angular velocity. So once we have this similarity analysis, we can come up with so-called pump scaling law, which is possible to experimentally determine the performance characteristic of one pump in the laboratory and then use this data to predict the corresponding characteristic for other pumps within the family under different operating condition. Okay, so under different operating condition mean that different Q, which is flow rate, and then different diameter. So there is the function of pump scaling laws. Okay, so now we move to in terms of special pump scaling law. Okay, so this is okay here. So for the special pump scaling law, okay, for the special pump scaling law, two special cases related to pump similitude commonly arise. Okay, so the first case, we are interested in how a change in the operating speed omega, which is the first case, special special pump scaling laws. Okay, so we interested with two conditions. The first one is what happen if omega is constant. Okay, what happen if what happen if we make a variation of omega? Okay, and then the same for the second case, what happened with variation of d, which is diameter, and then variation of omega, which is operating speed. Okay, so now let's say we for the so for example, the first one, Q1 over Q2 equal to omega 1 omega 2, and then in terms of we want to define in terms of actual head rise, which is HA1 over HA2 equal to omega 1 square omega 2 square, and then in terms of power coefficient, which is W dot shaft 1 divided by W dot shaft 2 equal to omega 1 power of 3 omega 2 power of 3. Okay, so this is for the second cases, which is variation of diameter. Okay, so this is variation of omega, mean that the diameter is similar. Okay, so we come out this equation. Okay, so d1 equal to d2. Okay, and then now for the second case, variation of diameter. Now we omega 1 equal to omega 2. Okay, so we change the diameter. So if we change the diameter, we come out with Q1 over Q2 D1 power of 3 over D2 power of 3 HA1 HA2 D1 square D2 square, and then the last one, power coefficient, W dot shaft 1 W dot shaft 2 equal to D1 5 power of 5 D2 power of 5. Okay, so this is pump scaling law. So from this equation, we can conclude that for a family of geometrically similar pumps, okay, geometrically similar pumps operating at a given speed omega 1 and the same flow coefficient, the flow varies as diameter cube. Okay, so for the same flow coefficient, diameter is cube, and then the head rise varies as diameter is squared, and the power varies as diameter raised to 5th power. So this scaling law relationship are based on the condition that as the impeller diameter is changed, all other important geometric variables are properly scaled to maintain geometric similarity. Okay, so this is pump dimensional parameter and similarity laws. Okay, the last one is an approximate empirical relationship to estimate the influence of diminished size on the efficiency. Okay, so 1 minus efficiency 2 divided by 1, okay, 1 minus efficiency pump 2 1 minus efficiency pump 1 equal to d1 d2 1 over 5th. So in general, it is to be expected that the similarity laws will not be very accurate if tests on a model pump with water are used to predict the performance of a prototype pump with a highly viscous fluid such as oil, because at the much smaller Reynolds number associated with the oil flow, the fluid physics involved is different from the higher Reynolds number flow associated with water. Okay, so that was for the dimensional parameter and similarity analysis. And then another important parameter for pump is known as specific speed, okay, ns. So ns, a useful python can be obtained by eliminating diameter d between the flow coefficient and the head rise coefficient. So this is accomplished by raising the flow coefficient to an exponent of 1 over 2 and dividing these results by the head coefficient raised to another appropriate exponent 3 over 4, so that the equation will be like this: ns equal to omega or n square root of q gh power of 3 over 4. So this is known as specific speed. So specific speed is the effective parameter that is used as an indicator for both performance and efficiency. So for pumps with low Q and high HP, which is head available, the specific speed is low compared to pump with high Q and low head for the pump. So pumps can be classified based on specific speed as follows. If the NS less than 1, it is known as radial flow pump. And then if NS in the range of 1 to 4, it is mixed flow pump. And then NS higher than 4, it is axial flow pump. So the last part for this specific speed is how to express based on the power. Okay, so based on W dot shaft, but how the NS is specific speed equal to n the square root of P over rho divided by GH power of 3 over 4. Okay, so that's all for palm dimensional analysis and similarity. And then the last important parameter, which is specific speed. See you in the next lecture for the turbine. Thank you.